So welcome back. So last time we had left off at this location where we were trying to use ImageJ. I had asked you to download this software, and I hope you have done that. Now what I'm going to do is I'm going to play around with one image, and I'm going to show you some of the features. I'm not going to, obviously ImageJ as a software has a lot of image processing capabilities, and this is not meant to be a tutorial on this. I just want to illustrate some of the points that we were discussing before. So what I've done here is I've opened this particular image right here, and you can see this ImageJ box is open here, and this is my window. Now it's a bit difficult to see, but here it tells you about the image type. So for me, it's, for example, I can read it out. It is it says 3084 into 5292 pixels. So it is telling me the m cross n that I just mentioned in the last lecture. And then it also tells me that this is an RGB type of image, so it has the word as letters RGB, and then it tells me the size of this, which is 62 MBs. That is not something we are interested in that much. But now as I move this cursor along, I hope you can see my cursor, which is a plus sign right now on the screen. As I move it around, you will see that there are some numbers that are going to appear right here, okay, in this region. Right now it is blank because I moved my cursor away from the image, but when I put the cursor on the image, certain numbers come up. So the first number corresponds to an x and y, and you can see that these are integer values. So these are going to change between different integers. What it is telling you is it's changing between right now it's both of them are integer values. One of them is greater than 1000, the other one is greater than 2000. Here this is the 0 0. If you take the cursor here, you can start seeing this is xy 0 0. So the image 0 0 is on the left top side of the image, and this is by convention that this is considered as the 0 0 of an image. So the image 0 0 is not at the bottom bottom left hand corner, which is what we usually do for, let's say, graphs. So this is the 0 0, and as you go along at the different x's y's, here the number, the first two numbers, they signify the x and y, and then it reads out the value. So it says x equal to some number, y equal to some number, comma, value equal to, and then in where I have kept it, it reads value is 69, 121, 181. These three numbers, what do they signify? They signify nothing else but the entries in the matrix. So we spoke about how basically you have matrices which will have those three values for R and G and B, and how those numbers must lie between 0 and 255. And that's exactly what is happening at some intermediate location. You get some value. Now there is a very bright section here. If I carry my my cursor to this particular location, now my first value has now maxed out to 255. The second two values, the second and the third value are very close. They are 253, 254, where I've kept my cursor. So it's almost saturated in this region, right? And you can see that how that looks up in the image. It's extremely bright. All the three RGB are present, and they are all almost equal. So it's the entire area is looking as white, right? Similarly, if you go to some other location, this is it has a more of a reddish tinge. You will see that the R value now is reading out to be 221, whereas the G and the B are 135 and 224 respectively. So you can see one of the colors starts to dominate over other, and you start seeing these nice beautiful colors. Similarly, you can go to other locations, and you will for example, at this location the blue dominates. So my cursor value reads 89, 162 and 231. So the blue value is larger than the R and the B values. Similarly, if you go to a location which is very dark and almost black, here for example I see a value of 3, 6 and 0. So this gives you an idea of how the image is, what this computer is rendering for me is basically nothing but a matrix with integer entries, right? That's a beautiful way of understanding images. Now just one second, I want to quickly see what are the, I am going to okay, histogram and this. Okay, so what I am going to do now, so now I can do a lot of different things here with the image, and some of the things include, for example, I will be able to wait just 1 second, I am going to find the correct. Okay, so if I go under analyze, I see there's a drop down menu, and one of the drop down menu reads histogram. So this when I do this, it is nothing but a histogram of the values between 0 and 255. You do not see R, G and B separately because it's sort of mixed together here into flattened out into a grayscale value. So you can, it tells you that this is the, on the y axis you have a relative frequency of sorts, relative frequency actually, and on the x axis you have the minimum and the maximum value that can be stored, again all integers. So these are bins, and if you plot this, it looks something like this curve. So it also tells you that there's a, for example, a fair bit of pixels with values close to 255 or saturation, right, which is what you also see in the image. There is saturation here. There's also images where, some pixels which are close to 0, and some of the other pixels they are all in between. Now if you wanted to see, for example, if I draw this rectangle here, and then I want to go to, let's say, image, and okay, wait a second, and yeah, no, sorry, if I go to analyze and then I say plot profile, okay, it plots out this curve for me. What it shows you, on the y axis you have the grayscale value, and this is your distance in pixels. So it is measuring the distance of pixels from your left hand side of the rectangle onto the right hand side, and it shows you that in the beginning you have this jari curve, and then you go up here. This flattens out, you can see this. This is your pixel saturation. So the pixels have saturated with the high value of 255. This is a grayscale value, by the way, so it's not really reading R, G and B separately. It's reading R, G and B as if it's all been merged into one. And then this starts to fall off later on. So you can get an idea of how the values in a particular row, for example in this image, how they are behaving with the values, and you can read it off from here, right. So basically an image is nothing but a two-dimensional matrix that we can read off. You can do a lot more things, obviously. For example, I'll come back to this in due time, but I just want to just go over what we did. Okay, so I have this. I showed it to you with the software, but now I've just I've done this before, just in case, and made sure that I've just taken screenshots of my screen before, and I wanted to show you these things again. So you can see on this side of the image, you can read out the number of pixels that are there. Then it says R, G and B. It tells you the number of megabytes this image occupies, and then if you keep your cursor at some point, it is not this image doesn't show you where the cursor is, but here the cursor is placed at this location, x equal to 1614, y equal to 2190, and then when you do that, it reads the value 255 for R, a value of 253 for G, and a value of 254 for B. So almost saturated, so it must be somewhere around this region perhaps, but you can read off the values with image like that. And then what we did is we went under analyze, and we looked at the histogram, and this is a grayscale normalization that you are doing, and here this is the values that are the bins from 0 to 255, and on this you have the y axis, you have the relative count, and this is a plot of the profile. And then we took a rectangle and then we saw how the grayscale value behaves. You saw this top off, right? This tells you that this pixel saturation that has happened, and this is not really that good, right? It's you shouldn't have pixel saturation. You have this signal could have looked something like this. It could have even looked like this, but that now is lost, that information, because of saturation. So saturation is not a good thing. You should avoid it. This what we are doing right now with respect to ImageJ, this can also be done using Matlab or some other software like Python. And one of the advantages of other softwares is that you can now start writing your own code. I mean, what you have is essentially a matrix, right? So if you can extract the matrix out, then you can start doing a lot of operations on them. So with a software like Matlab, you will be able to go in and you will be able to read the matrix in. So what I've done is I have done this myself. We have a copy of Matlab in my system, and I went ahead and I have done some of these, and some of these commands I have written down for you so that you might want to use it. If you do not have subscription to Matlab, you can also use open source softwares like Python. You'll need an appropriate image processing toolbox to be able to handle images, but you should be able to do something similar over there. So what I've done here now, I have used the same image that I've shown you with ImageJ, and I have read it using the command called imread. Okay, so imread is image read basically, and I have read it so that I have called my matrix I as imread whatever my name, right, of the image. In this case it is Orion Nebula for class.jpg. And then what it does is once you enter this command, it will, so the image is obviously in the same folder in which I am operating. So it reads that and it tells you here what it does. So I now is a matrix with m cross n, where m is 5292, and then this it also tells you the other value, and then it tells you into 3. So this tells you that the image is a color image, right? So this is a color image. But I've told you before, for many of our work, we actually don't have to use color images. We are good with monochrome images. So these color images are not always necessary. For many of our analysis, we'll see, actually for almost all our analysis, we'll see monochrome images are as good. So what I want to do is now, although the camera was a color camera, I want to convert everything to monochrome. If your camera itself is monochrome, you will not get a m into n into 3 matrix. You'll just get an m into n matrix. But in our case, we have this was from a color camera. So what I do is I write this command called igray, which is the name of a matrix, and then the actual command is rgb2gray. And as an input, I give it the I matrix, which I've already read and defined before. So now my I gray becomes an m into n matrix. And you can see it here on this side. It's the workspace is displayed. It says I gray and it says m into n, and there's u int 8. Okay, so this is 8-bit. It signifies that this is an 8-bit image. You can use tool commands like imtool, and when I do imtool and I put igray as my input, it reads this matrix igray and it renders it for you again as an image, right, which is what you often want to do. Once you do that, this ends up like, you'll end up like a box like this, where Matlab has rendered the matrix as an image. And this is what it looks like, and I have my cursor again somewhere, and the cursor is at this location 155133494, and it tells me that there's a grayscale value of 251 at that location. So it's similar to the operation that we are doing at the ImageJ, where we are just changing our cursor location and we could read off the value at that place, right. So these are very good tools. Now, okay. So before I go to this part, I want to explain a few things. So we go back to our notes. Okay. Now you saw that there are different ways in which you can different softwares that you can use. With a software like the ones I was using later, Matlab, I could read the entire image as a matrix. So basically, your images. So once you have access to the matrix, which represents the image, there are a lot of algebraic operations you can do. And this is interesting and very important. Okay. So for example, okay, let's say you had two images. Okay. So you have two images, I1 and I2, and you want to define a new image which is the sum. Then all you have to do is just say you have to define a new variable called isum, and you just say it is my matrix I1 plus I2, and you just do a matrix addition, and there you have it. Right. So this is, you can see, hopefully you can begin to see what kind of a powerful tool now you have once you have access to the actual matrix, right. So now, for example, if you wanted to do a background image subtraction, when I mean background, what I mean is this a commonality between, let's say, background image subtraction for a sequence of n images, okay, n images, which means you have images I1, I2, I3 all the way up till In, and what you wanted to do is to figure out what is the exact commonality between all of them and subtract that out. Then what you could define is as a new averaged I. So let's say you want to do it from the ith image. So what I'll do is I'll do this particular algebraic operation where I define an averaged I as sorry, background subtracted I. This is not an average. So this is some my I dash, okay, is equal to II minus 1 by n II summed over all i's. So you could easily write this command and get this new matrix, and this new matrix will be now a background subtracted image. Okay. You can define other types of background subtraction also. I am just defining one particular type, and you can see my motivation for doing that. And let's say you wanted to increase brightness. Okay, so let's say increase brightness or change the brightness of an image. Then you define a new I dash as being equal to C times of I. Okay, where C is a number is not 0, is greater than 0. Then for C less than 1, between 0, you will get I dash, which is okay, let me put this here, sorry. So if C is less than 1, then image becomes dimmed, right. So the values are smaller, so you are closer to the 0, which is basically is dimmed. If C is greater than 1, then brightness is increased. There are obviously other types of algebraic equations, algebraic operations you could do. You could multiply it with a c square, you could multiply with c cube, or some other function you want to desire. But I am just giving you out to the most simplest of things you can do. Okay. Now, another important thing that is often done with respect to images is, let's say, okay, so let's say this is your this is 0 and this is what I'm going to draw is the image histogram. So this is 0 and this is 255. Okay, let's say the original image is such that what you have is a histogram something like this. Okay, so and this is obviously relative, y axis is some type of relative frequency. I am not writing it down for the second graph, it is the same thing. Okay. Then what you could do is you could map this old image to a new image such that this histogram now changes, and you end up with a curve like this. Okay. And what I have done is, whatever this value was, let us say this was some 50, and let us say this is some 220. Then I have stretched it out so that in the new image my 50 now corresponds to 0, and this 220 now corresponds to 255. So you could use tools, for example, there are good tools like Photoshop which will allow you to do this kind of histogram stretching, and this is also called contrast stretching. The image at the bottom has a better contrast than the image at the top, and that is just done through managing the relative histogram, and that you can do by changing the transfer function. That allows, that is something tools that are there in many different softwares. Now ImageJ also allows you to do that, and just let's take a look at how you might want to do something of that sort. So let's just use ImageJ, and let's say you have this image, and what I'm going to do is there is two ways. Just a second, I'm going to try and find. Okay, so if I go here under process, it allows me to do something called enhance contrast. Okay, then it asks me for a number here. Maybe I'll just change. Okay, before I do this, 1 second, I want to have the histogram so that we can show the difference. Okay, and I had found the histograms where, so here. Okay, so this is the histogram of the original image. Now if I go in and if I change, let's say, so maybe I'll just go here and I'll do enhance contrast, and maybe I'll put some other number, some 10. I'll do an equalize histogram. This hasn't changed the image much. Maybe do, or maybe not do the equalize histogram. It's not changing this image a whole lot. Okay, I'll think I'm not able to find the exact. It appears that the version I have on my computer versus the version here is slightly different. Okay, so if you go ahead and start making certain changes to this image, yeah, if you look here, what it allows you to do, you can see there's a lot of different mathematical operations it allows you to do. Math, you have add, subtract, multiply, divide. Now, if you were wondering before, if you did not know the background of how images actually are, they're just matrices, this could set you off as to what exactly is happening. But now that you know what are the things you can, what is actually probably happening right behind the back in the software. You can also do Fourier analysis. Again, since it's just a set of numbers, you can do that. And there's a lot of other things you can do. For example, it allows you to do Gaussian blur and all that, and convolutions and all. So if I try to do a Gaussian blur, let's say 50, right? Okay, this, oh, it's showing up here. Okay, I don't know why I tried to do a Gaussian blur there. Wait. No, it is under math. Yeah, sorry. Gaussian blur. Okay, so you see this image has now gotten blurred, right? So the blurring process has done that. And if you go now and look at histogram, your histogram you see here is very different than the one you started out with. So the mathematical operation that you did on this has effectively changed the histogram quite a bit. So there are different, in image processing you want to be able to control this kind of a process. You want to be able to know exactly what type of histogram you want, and that sometimes comes from the exact operation you want to do sort of depends upon the exact need that you have, which is very situation dependent. Now I'm just going to go over some of the basic ones that we usually do, and there's one more. This is 4, so maybe I'll just do another one. There is a very common operation that people do, which is called thresholding. Now the thresholding also you can define a complicated algorithm for that, but usually a simple thresholding operation is you look at the pixel value and you define a certain threshold, and if the value at that pixel, okay, at that particular pixel is greater than the threshold, then you set the value of pixel to the max. So in this case it is 255, right? So else, so if it is not greater than the threshold, then you set the value to be 0. And this algorithm gives you thresholding of a certain type. You can of course define different types of thresholding also. So you could potentially define a thresholding where you leave the pixel value as is if it is below the threshold, or you need not have to go it to the maximum, right? Your threshold value could be different for R, G, B, etc. So there are different types of thresholding operations you can define. This is the simplest type, and how you should the question I would ask is, how do you visualize this kind of an operation graphically? So I leave that problem to you to check out how to do that. Now when you have a matrix like this, one very important operation that we do in image processing is something called convolution. Now convolution you may or may not be familiar with, but so if you are not familiar with it, give a very brief quick introduction to convolution. Okay, so let us assume so you have a linear passive and time invariant system. Time invariant meaning how it is changing the input and output. So let's say you have a system like that. The system is going to be represented by this box, okay, and in this I feed a certain input function called ft. This is my input function, and I want a certain output function, or I get a certain output function from the system. And what kind of a system is this? It is linear, passive, and time invariant system. Then if I had to calculate this fyt for an arbitrary input ft, then what is usually done is you do this same experiment, but first you feed it the delta or the impulse function, okay, as an input, and you should get some output, right. So this is also called the impulse response. Okay. Now once you have this, theory says that my yt, which is my output that I wanted to calculate, this is given as a convolution between this impulse response function and my ft. Okay. Now in the case of continuous functions, this convolution is defined as this integral, where this goes from minus infinity to plus infinity, my tau. So I define a dummy variable for myself, and this is now becomes f tau, and this becomes h t minus tau d tau. Okay. I am not going to go into the details of how this really comes about, because that goes into the theoretical idea. But if you had to think of it simplistically, what basically it's doing is it's evaluating the impulse response function and then deciding that, okay, my response is nothing but this summed over in an integral sense, it's summed over the input function ft, ht summed multiplied with ft, and that sort of summed over in an integral sense. Now this is for a continuous case. For discrete cases, my convolution, okay, is defined as nothing but, let us say I now define a new variable I, which goes from minus infinity again to plus infinity, and this is my fi. So this is my fi, and this is my h again, t minus I. Yeah. Now interestingly, when you have causal systems, the upper limit in this integrals cannot go up till infinity. Okay. So in causal systems, this upper limit is restricted to t in causal systems, which means that my future, so if you integrate from minus infinity to plus infinity, if you are thinking of tau as a time thing, then your future functions are impacting the current, and that you don't allow. So then you restrict the top here to t, and similarly in this particular case, right. So there are different properties of convolution, and they are because integration is a linear operation, you have many of the properties of linear operations that reflect in convolution. So f convoluted with g is the same as g convoluted with f. So this is I hope you remember this kind of behavior when we are discussing some other mathematical preliminaries. Similarly, if there are three functions where f is convolved with a convolution of g and h, then the order does not matter. I could have as well as convolved f and g first, and then convolve that with h, and that will be the same thing. Similarly, if you are multiplying f with some scalar alpha and convolving alpha f with g, then it doesn't matter where you multiply the alpha. So the same. So alpha f convolution g is the same thing as alpha f convolved convolved with g, or f convolved with alpha times g. So this all comes because you have a linear operation at hand. Why are we discussing this? Obviously because we are going to start convolution with the image matrix, right? So images also allow, you can do convolution operations with matrices, but before we understand convolution operations with matrices, we should understand convolution operations with vectors. So let's say we want to do a vector convolution. Where let's say you have a vector, a row vector, A is a row vector with m entries, and B is another row vector with n entries. Okay. So you have two vectors with different number of elements. So basically your A looks something like this, where you have A1 all the way till AM, and B is B1 all the way till Bn. And we want to do a convolution operation of these. So the convolution operation of these two gives me another vector, and this vector is essentially another vector with C1 some elements. Now you have to find a rule which gives you this, and the rule is that such that or rather where every element, so if I have to give the jth element of my C vector, that can be found as integral of summation of ai into b I j minus I. This is my j minus I. This I am doing just simply by sort of copying the discrete version right here, except that now since these are vectors, I have to do a +1, because the 0th element doesn't mean anything with respect to vectors. The first element is 1, so I have to do a +1, and this is I from all the way minus infinity to the element j, okay, for causality. So and with the notation that where I ranges over all values, all legal values. So I cannot have minus infinity, because when I am dealing with vectors, there's no entry called minus infinity there. You have entries from 1, 2, 3, 4, right? So you cannot take arbitrary i's. That's what it means. Okay. Similarly, you can do a convolution of vector of matrices. Now, two-dimensional, so 2D convolution, discrete convolution looks like this. F convolved with G, let's say x comma y. I'm going to run out of variables to name. So let's say the 2D here you have f and x and y in the convolution, and on this side you are using I and j as the entries. So then I will say I comma j, and now these are the dummy entries because I'm going to sum over I and j. So this is I and j, all possible values of I and j, and on this side you have x minus I and y minus j. So now you can do this, you can use this formula for 2D discrete convolution. You can apply that for matrices. Once again, just as we did before, here we had to do a +1, you would have to do something similar. Now once you do that, you can actually do the summation and get the convolution for 2 matrices if you had to do that operation. And you can do convolution operations in softwares like Matlab, where Matlab allows a particular command called conv2, C-O-N-V-2. I will show it in the next class, and that operation allows you to convolve 2 matrices or even 2 vectors. Conv2 I think is for matrices and conv is for vectors. I'll have to look that up, but I urge you guys to also take a look and see which commands, if you are using something like Python, what are the commands for in that particular case. And I'd like you to go ahead and try some discrete convolution yourself, so that when I'm explaining convolution operation on images, it will you'll be better able to understand and follow. So for today's class, I'm going to stop here, and in the next class we are going to look at convolution, some examples of convolution specifically for images. And yeah, with that I will end today's class. Okay, thank you.